numbers. Yeah, they got really lucky, like by about a day, I think, 'cause it's supposed to get really bad. I don't know. I just don't. About most. Somebody, I'm sure. I'm sure they're nice people, and their mothers love them. Okay. I'm sure. Let's see. Ashley, no. Lindsay, no. Lindsay, no. She's Jessica. Here you go. No. Bonnie, go. Jen, no. Richard. Thank you, sir. Jared. See, Jared. Will. Sarah. Go. Diana. Devin. John, no. Okay. Okay, let's see. Chris, no. No. Okay. Not too bad. Couple of quick comments on the assignment coming back. Most of them were pretty computational, so didn't cause too much grief. The only issue that came up on the more computational stuff is what that one question asks you to do is find a generator for, not for Z17. Well, I know what a generator is for Z17 as an additive group. Just one works because 1 plus 1 is 2. 1 plus, so that's not an issue. What is at issue is this. If you look at the non-zero elements, look, 17 is prime, so Z17 is a field, so the non-zero elements form a group under multiplication. That group has 16 elements in it. Is that a cyclic group? Well, if somebody just hands you a group with 16 elements and tells you it's abelian, there's absolutely no guarantee that it's cyclic. But what will be shown, we won't do it this semester, but we will do it next semester. If you come back for another dose, then you'll find that if you take any primes and you take the field Z sub that prime and you throw out 0 and you look at the corresponding abelian group, that group is always cyclic. So what you're trying to do is find a generator for this under multiplication. That's the question. The other way to phrase it is, in other words, take the units of Z17. And as soon as you're told that you're supposed to be looking at the units of Z17, it means you're throwing out 0. And so necessarily you're looking at times as the operation. A couple of you just convinced me that Z17 under addition is cyclic, and that certainly could have been done about 2 months ago. You just write down the number 1 and show that if you keep going, you get all the elements in Z17. So a couple of you misinterpreted that question. The other one that caused some of you some grief was the last one. In effect, what you're asked to do is this. Take the following function from a polynomial ring to another polynomial ring, the function that what we call formally differentiates polynomials. Well, you come into the table knowing something about differentiation, but only in a situation where the coefficients come from the real numbers. And in that particular situation, differentiation of polynomials is just one of many differentiation ideas that you can talk about. You can talk about, differentiation in the context of exponential functions or trigonometric functions or whatever it is. And just as one sort of byproduct of differentiation happening to mean limit as h goes to 0, blah, 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 you happen to get this particular formula for polynomials. But the point is that formula can be thought of as a formula that applies to any polynomial over any field of coefficients. Take a polynomial and simply associate it with this other polynomial. Take the polynomial a0 plus a1x plus a2x squared plus da 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 and associate it with, I'm just going to make this thing up. A1 plus 2 times A2x plus 3 times A3x squared plus 4 times A. Makes sense. The fact that it happens to be apparently interesting because it happens to be this byproduct of a formula that comes from a limit expression, okay, it just happens to be. But folks, this formula has nothing to do with limits or anything. It's just do it. And with that in mind, the question then becomes part A, is this a, well, is it a homomorphism where the operation is addition? You're thinking, well, you know, if I was working over the reals in the particular case where the field is R, then yeah, because the derivative of the sum of two functions is the sum of the derivatives. There's an addition rule. Question 1, part B was, is the derivative function somehow a multiplicative function? In other words, is the derivative of f times g the derivative of f times the derivative of g? And you should have been thinking right away, well, no, because derivatives and multiplication don't work out well. There is the product rule that doesn't say just derivative of f times derivative of g. And most of you recognize that. That's good. Some of you wrote this sort of flowing prose about how it shouldn't be and it's not and there's not a prod, blah, 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 blah. But just, folks, give me a counterexample. Just write one down and you're done. That's all you need. Okay? All right, now, parts B and C were interesting. I guess I should have known that I'd get this. You know, I mentioned in class, well, you need to use the characteristic of the field as 0 in parts B and C, and some of you just started off parts B and C saying because the characteristic of the field is 0, and just went on and basically didn't at all use the characteristic of the field is 0. It's all right. Or some of you sort of put it in, but it sort of appeared at a place that indicated that maybe you weren't really using it in a way that was that compelled me to believe that you understood what was going on. Here's the idea. What things are in the kernel of the derivative function? That's the idea. And if you come to the table thinking, well, I know what things the derivative function kills. The derivative kills constants. Perfect. Okay, it's just we're taking the derivative in contexts that are larger than the one that maybe you're used to working with. You're taking derivatives in the context that isn't just r bracket x, which has a certain set of properties associated with it. You're taking derivatives presumably where the field could be anything of characteristic 0. Maybe the field's the complex numbers. Maybe the field's the rational numbers. Maybe the field are some other fields that we've seen. For instance, this thing that we called S, the a plus b root 2 field. So how do you know that the only thing that gets killed in that context are the constants? It's not anything to do with a limit process anymore. And the answer is this. Just write down what it means for something to be in the kernel and convince me that it has to be a constant. So what does it mean for a polynomial to be in the kernel of the derivative function? It means if you write f of x as a0 plus a1x plus a2x squared plus a n x to the n, that's what it looks like, then the derivative is, well, it's a1 plus 2 times a2x plus 3a3x squared plus et cetera, plus n a n x to the n minus 1. There's the derivative. No problem. And the question is, what does it mean to say that the polynomial is in the kernel? It means that the derivative is 0. Equals 0. That's what it means by definition of it being in the kernel. So look, I have this polynomial equaling this polynomial. So all the coefficients have to be the same. That's how two polynomials are equal. Well, let's see, the coefficient on the constant term over here is a1. The coefficient on the constant term over there is 0. So we get a1 is 0. The coefficient on the x term over here is 2 times a2, and the coefficient on the x term over there is 0. Coefficient on the x squared term over here is, and the coefficient on the x term over there is, et cetera, et cetera, et cetera. The coefficient on the x to the n minus 1 term is that. The coefficient on the x to the n minus 1 term on the right side is 0. I mean, obviously, they're all 0 on the right-hand side. So I'll say equate coefficients, because that's what it means for polynomials to be equal. So here's what this says. If f is in the kernel, then necessarily the constant term is 0. Okay. Ah, I said that wrong. If the derivative is 0, then necessarily the linear term is 0. In other words, the term that's being multiplied times the x term is 0. If f is in the kernel, it means that 2 times a2 is 0. Question, does that imply that a2 equals 0? I'll give you a hint. And I'll give you a hint. Use the hypothesis. Why? Look, if you have the product of two things equaling 0, any field's an integral domain, so one or the other has to be 0. Is this equal to 0? No. Why? Because the characteristic of the field is 0. 2 is not 0 in our field because we're told that inside this field, if you take 1 and you keep adding it to itself, you never get 0. In particular, 2 isn't 0. So it implies a2 is 0 since the characteristic of the field is 0. How about 3 times a3? So that's 0. Does that imply a3 is 0? Sure does. Why? Because the characteristic of the field is 0. I have n times an is 0. That implies that an is 0. Why? Because the characteristic of the field is 0. So here's where you're using the hypothesis. So what we've just shown is that if you take something that's in the kernel, then necessarily a1 is 0, a2 is 0, a3 is 0, etc. up through an is 0. In other words, if you have something in the kernel, then all this stuff has to be 0, because we've just proved that each of the coefficients is 0. So if you have something in the kernel, it has to look like just that. In other words, it has to be a constant. So essentially, all of you got to the right place, but you didn't use the place where the characteristic of the field is 0 appropriately. Okay, now for part C, I'll go through this one a little bit more quickly. Most of you recognize that the image, in other words, what actually gets spit out of the derivative, is every possible polynomial. In other words, you told me the image is all of f bracket x. Well, that's true. Let's see what happens in the reals. If you hand me a polynomial, you have to convince me there's some other polynomial whose derivative is the one you started with. That's what it means to convince me that the range is all of f bracket x. Just as an example, if I hand you x squared, can you build me a polynomial whose derivative is x squared? Yeah, you integrate. 1/3 x cubed works. I mean, 1/3 x cubed plus 7 works. There's lots of different integrals. But just write down an integral. 1/3 x cubed. Derivative of 1/3 x cubed is x squared. So x squared is in the image. You know, x to the fifth is, in fact, x to the n is in the image because I can write down something whose derivative is x to the n. 1 over n plus 1, x to the n plus 1. I'm just integrating. So you take the derivative of the integral and you get right back where you started. So that all seems well and good, except for what? Except for how do you know that 1 over n plus 1 times x to the n plus 1 makes sense? In particular, how do you know that 1 over n plus 1 is a legit thing to write down? I'll ask it one more way. How do you know that 1 over n plus 1 isn't 1 over 0? And the answer is because the characteristic field is 0, that n plus 1 is not 0. So the punchline is, because we have a field of characteristic 0, we can, quote-unquote, integrate any polynomial. So the point is that for part C, to show that every f of x is in the image of D, image of the derivative, if f of x is blah, 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 then, so as above, then write down this. G of x as, what is it, a0x plus a1 x squared over 2 plus a2x cubed over 3 plus an I just, in some sense, artificially pulled out of thin air some polynomial. This is in f bracket x. The reason it's in f bracket x is because each of these symbols makes sense because none of them requires me to divide by 0 because none of the denominators are 0 in f because the characteristic of f is 0. Okay, since characteristic of f is 0. So none of the denominators is 0, and you can show that the derivative of g is f. And so every polynomial little f of x is in the image. If the question is, well, what if you couldn't do this? What if, for instance, you were working in the field z2x? Can you divide by 2? No. So what that means is that there are polynomials in z2 bracket x that you can't integrate. In other words, that you can't find a polynomial for which, when you take its derivative, you get the original one. I'll give you a good example. Try to find for me a polynomial whose derivative is x, where you're working over the field z2. Find a polynomial. How about x squared? That's no good, because its derivative is 0. It's 2 times x, but 2 times x is 0. You say, well, divide by 2. You can't divide by 2, because 2 is 0. So that's what's going on, and that's what a couple of you picked up on, and that was good, but some of you just sort of threw down characteristic of f is 0, and we're happy with that and went on. All right, well, I mean, you're listening, so I can't fault you for that. That's good, but there was a little bit more to that. Okay, here's what we're up to tonight. There's two. Oh, let me just make sure I do some administrative stuff that I need to do here. Yeah, the administrative stuff is after the break. We're meeting in where? Dwyer 121. So I don't know. Are you on next Monday?
Yeah, I thought it was today.
Oh, oops.
That's why I interpreted the email, but
Oh, I'm sorry.
I'll make sure they know.
Okay, thanks. Maybe that's where everybody is. Oh, I take back all the bad things I said. Maybe they're up at Dwyer 121 instead of Mile High Stadium, but that's okay. No, or not. And right, if you want to turn in the homework tomorrow, you can do so. That's fine. Just fax it to me by, let's say, 5 o'clock tomorrow or so, or email it to me as an attachment. That's probably the preferred mode. What we're up to tonight is we're going to finish up some sort of final tidbits about irreducibility of polynomials. We'll spend 10 minutes or so talking about the main goal for the remainder of the semester. It will give some good context to what we've been doing for the last 2 weeks or so in this discussion of polynomials and polynomials over various fields. And then we'll start sort of heading up the path towards the final summit for the semester and start building the tools we need to actually get to this main goal. So here's some sort of final tidbits on factorization and irreducibility. Final stuff on factors, irreducibility, etc. The first is last Wednesday's presentation was unlike one you've seen before probably in any math class, because it was essentially just this sort of ad hoc list of here's the big question. Tell me, if you hand me a polynomial with coefficients in the following field, is it or is it not irreducible in f bracket x, where f is the given field? And the answer is just that there's just no good, hard, fast rule that always works. You have to use some methods that are specific to various fields, or specific to the degree of the polynomial, or specific to the form of the polynomial. And we just don't have that many general results. A lot of times it's just a matter of taking whatever polynomial you're looking at and just trying to haul out whatever tools you might have at your disposal. So that's why the last Wednesday looked a little bit odd, and why this homework assignment that's coming in today or tomorrow was just, you sort of had to look at it and say, well, what field is it in? What's the degree of the polynomial? What do the coefficients look like, et cetera, to decide what test to use. Here's one last irreducibility criterion that I didn't mention last Wednesday, and it's this. These are called cyclotomic polynomials, and even though they look like a very special form, they come up relatively often in a specific context that those of you that are going to take the Math 4/515 course next semester will see. It turns out if you hand me a polynomial, it looks like this. F of x equals x to the, make sure I've got his notation. It's either p minus 1 or p, depending on where you want to start here. Yeah. If you look at x to the p minus 1 plus x to the p minus 2 plus x squared plus x plus 1, where p is a prime, So for example, you might be looking at, if p is 5, x to the 4th plus x cubed plus x squared plus x plus 1, that polynomial is irreducible in q bracket x. I didn't prove much for you last Wednesday, and other than the results about degree 2 and degree 3 polynomials, but a lot of these are just ad hoc, so you can add that one to the list. Here's another one. If you happen to see a polynomial of this form, then this happens to be irreducible in Q bracket X. All right, that's the first comment. Second is this. I've been trying to play up the similarities between these rings F bracket X, the polynomial rings, and the integers, and we've seen lots of similarities. Neither is a field. Both is an integral domain. Both have division algorithms associated with them. Both have the property that inside them we can talk about some sort of notion of primeness or irreducibility. We call it prime in the integers. We call it irreducibility in the context of polynomials, and those two ideas are essentially the same. And the last comment is, for the integers, at least if you start with non-zero integers, in fact, let me be a little bit more precise. If you start with an integer that's not -1, 0, or 1, so if you start with not 0 but not a unit, then it turns out you can always take such a thing, and either the thing is already a prime, or if it's not prime, you can always write it as a product of primes. That's what we call the fundamental theorem of arithmetic. And moreover, if you somehow line up the primes in increasing order, there's really only one way to do that. So if somebody hands you and your friend the same integer bigger than or equal to 2 and puts it in separate rooms and says, write this as a product of prime numbers, well, you can do it. And in fact, you'll both do it the same way. Of course, if somebody hands you 6, you could write as 2 times 3, and your friend could write as 3 times 2. But, if you agree to write them in increasing order, then in fact, there's only one way to do it. And the punchline is the sort of last similarity that I want to point out between the integers and the polynomials is there's a similar sort of result for polynomials vis-a-vis writing polynomials as products of irreducibles. So the remark is the analogy between F bracket X and Z sort of continues, has another, piece to it. It's this, the analog to, I'll write down what it's called, at least for the integers, fundamental theorem of arithmetic. Theorem of arithmetic says this essentially for F bracket X, given any little f of x in cap f of x whose degree is bigger than or equal to 1, with the degree of f of x at least 1, then there is, I'll say essentially because I don't want to get into the details, but I'll at least give you the analogy of why I have to use this word essentially, a unique way to write f of x as g1 of x times g2 of x times g sub t of x, where each g sub I is irreducible in F bracket x. G sub I of x is irreducible in F bracket x for all I. For all I. In other words, any polynomial, as long as it's a polynomial with some guts, just don't hand me a constant polynomial. Give me a polynomial, you can always write it as a product of irreducible polynomials. And moreover, if you and your friend try to write it as a product of irreducible polynomials, well, it's like here, if I ask you to write, 14 as a product of primes, well, technically you could write it as 7 times 2. Or you could write it as -7 times -2, because remember, inside the integers viewed as a ring, we have to include the negatives, and we have to include negative numbers as prime numbers. It's the same thing here. You might take x squared minus 1 and write it as x plus 1 times x minus 1. Okay, that's good. But your friend might write it as 2x minus 2 times a half x minus a half, or something like that. I mean, if you got enough fractions around, you can sort of mess it. Yeah, but all right. The idea is you can just yank the constants out, and what you're left with is essentially the same. So that's what's going on. I definitely don't want to spend the time or the energy to write up this statement precisely, and I'm certainly not going to ask you to kick it back at me or have it on exam 3. But just know that there really is this very tight relationship between what's going on inside the integers and what's going on inside of f bracket x. The only real non-similarity between what's going on inside the integers and what's going on in f bracket x has come up in this question of how do you find whether or not polynomials are irreducible in the given field, and that happens to depend on the field and the polynomial, etc. And we don't really have that sort of behavior happening inside the integers. Okay. Now, 2 final comments, not about polynomials, but rather about fields in general. We have not, folks, and won't get to this semester, maybe next semester, but we won't get to this semester, an example of the following form. All of the, remember what are called skew fields or division rings. They are rings with the property that when you throw out 0, that what's left over is a group. That's all that's required. All of the examples that we've shown of such a structure has always had the property that when you throw out 0, not only do you get a group, but you get an abelian group. In other words, the multiplication has been commutative. There are examples of rings with the property that when you throw 0 out, you actually do get a group under multiplication. But it isn't a commutative group. It isn't an abelian group. Those are called division rings or skew fields. And it would take us a half hour to 45 minutes to write down all the details of the example. So I'm going to leave that out. And suffice it to say, they're out there. But we just got to work a little bit harder to find those. And the last comment about fields before we move on is this. The only finite fields that we've looked at so far, that is, the only fields with the property that they contain only finitely many elements, are the z sub p fields. So there's a lot of them. But it turns out there are many other fields having finitely many elements that aren't just z sub p. And we'll actually get to those. That'll be one of the final goals in this class. We'll be able to write down fields, for example, that have 4 elements. You're thinking, well, Z4? No, Z4 is not a field. It has 0 divisors. It can't be a field. 2 times 2 is 0. But it turns out there's another ring out there that has 4 elements. And it turns out it has the property that if you throw out 0, that what's left over is a group having 3 elements. Okay? It's not Z4. It's something else we haven't seen yet, something else we're going to have to build. But they're out there. So the remark is there are finite fields which are not of the form z sub p, p prime. We haven't seen any of those yet, but we'll see one by the end of the semester. We'll see some by semester's end. Okay. Well, maybe surprisingly, no. I mean, I shouldn't put it this way. I could, tonight, write down the ring. I could tell, write down the 4 elements. I could tell you what the addition operation is just by giving you a table. I could tell you what the multiplication operation is just by giving you a table. But it would make no sense. It would just sort of look like, gobbledygook. And what we'll be able to do by semester's end is actually, quite naturally, in fact, sort of lead ourselves to that sort of structure. And not only with 4 elements, but with 8 elements, or 16 elements, or 9 elements, or 27 elements, or a prime power number of elements. Okay. So here's a big aside. I'm going to call this is what the author calls it, the basic goal. So here's a 5-minute whirlwind history of what has motivated much of mathematics for the last, almost 2,500 years now. You look at a certain system, you get comfortable with an operation in the system, and then you realize the system somehow isn't big enough to allow you to solve all the possible equations that might come up in that system. Here's a good example. If I'm looking only at the positive integers, which, you know, the sort of basic natural numbers, the counting numbers, if I hand you an equation that has something to do with addition, so if the system is the positive whole numbers, positive integers, and the operation is addition, and I ask you to solve an equation of this type, you're golden. I mean, x is 4, it's no big deal, you can solve it in the system. The problem is, though, if I ask you to solve this equation in the same system, you obviously can't solve it in the system of positive integers. That's sort of unfortunate. So what do you have to do? Well, if you want to somehow allow yourself to solve all the possible equations that might come up in the system that you started in with the operation that you're interested in, you might have to invent or cook up new symbols or new numbers that behave in a way that would allow you to solve systems of this type or equations of this type. So I'll say OK in z plus, but this is not OK in z plus, meaning there is no solution in z plus. And, you know, we're so comfortable with it, especially as math majors, but even by, you know, 6th grade or something, you're comfortable enough with the idea of a negative whole number. It's simply a symbol that, in effect, allows you to solve an equation like this. It allows you to go backwards. But this is OK in an extended version of z plus. We call it z, i.e. z. And in effect, you invent symbols, the negatives, which behave well, which do what you want to do what you want them to do, namely solve equations of this type. So we wind up with a nice system, you know, as far as it goes. So whole numbers sort of become entire or become whole if you allow the negative numbers, because then you can solve any equation that looks like this. That's good. Of course, then what do you want to do? Well, if you turn your sights to a different operation, multiplication, you try playing the same game. And if somebody asks you to solve this, 3x, you know, equals, I don't know, 12 in z, solve that in the system that we're now working in the integers, no problem. X equals 4. But solve this in z. And the point is, folks, all of the symbols that you're writing down are coming from your underlying system. And the operation is one that's of interest in the underlying system, multiplication. It's just you can write down equations that, you know, in some sense look just like this. It's just instead of the operation addition, you've written down the operation multiplication. And obviously not OK. Can't solve it in the integer. So what do? You invent a system that contains solutions to all the equations that look like this. And that system is called the rational numbers. So you extend, you invent symbols that do what you want them to do. Rationals. And now you've got a bigger system. And inside that bigger system, not only can you solve any equation that came from the original system that looks like this, you can actually solve any equation that comes from the bigger system. So if you want me to solve 3/7 x equals 19/4, you can do that in the bigger system, the rationals. Now we have a bigger system. But then we ask similar questions like, all right, now instead of taking just linear equations, x plus 3 equals 7, so linear in addition, or 3x equals 12, linear multiplication, take maybe quadratic equations like this. Let's do this. X squared equals 9. So now I'm asking you, if you want, just view this as x times x. I mean, I'm still asking you to take the multiplication operation, but now instead of having you look at a constant times x, now I want you to look at a variable times itself. Can you solve an equation that sets that equal? Well, sure, that's of course okay. It might be more than one solution, plus or minus 3. That's no big deal. But then if I ask you to solve this, well, inside this system, no good. And the Greeks already knew that the rationals weren't big enough to allow them to write down a solution to this equation, to the x squared equals 2 equation, because the solution was square root of 2. And Euclid wrestled with that. He proved that you can't solve this equation inside the rationals. So that's 2,000 years ago. So what did they do? They invented some numbers that made the system whole again, that included solutions to these things. Now that's a little bit of a larger leap. It wasn't just write down all the fractions or write down all the negatives. All right, write down a system where you have a square root of 2. Well, one way to do that is to, in effect, write down that ring S that we talked about, a plus b root 2. Just cook up a symbol, invent symbols like the square root of 2. That's all it is. And then you've got a solution to that thing. Of course, if you also want a solution to x squared equals 3 or x squared equals 7 or x squared equals 11 in this same system, you have to sort of keep bundling stuff on. And so eventually, fast forward 1,800 years or so, eventually you invent the real numbers, sort of rigorously invent the real numbers. Most people played with them and sort of knew what their properties were, but it wasn't until Kronecker came along, or Dedekind came along and sort of did this Dedekind cut approach to the real numbers as limits of appropriate sequences of rational numbers. All right, so you invent a system where you can solve equations that look like that. Of course, even with all that work, you still left some things out, like solve that. No good. I mean, you still need to go bigger. So you invent some symbols. That symbol. And it behaves the way you want it to. And so you sort of, over 2,000 or 2,500 years has been sort of piling on of different levels, different levels, different levels. And eventually what we get to is a system called the complex numbers. And it turns out, well, one of the fundamental properties of the complex numbers is that if you hand me not only linear equations or quadratic equations, if you hand me any polynomial equation, a n x to the n plus a n minus 1 x to the n, blah, blah, and you set it equal to 0, you can always find a solution for it in the complex numbers. So somehow the complex numbers is as big as you need it to be. It's a phrase that we'll use next semester. It's called algebraically closed. Any polynomial that you write down, if the coefficients come from here, you can always find a solution to it in the complex numbers. That's not true of any of the previous systems that we've written down. Okay? All right. What I'm going to focus on, though, is this. If I want a system that, let's say, contains at least the rational numbers so that I can at least do the basic operations, addition, subtraction, multiplication, and division on the whole numbers inside my system, that's how I get the rational numbers. If I want to solve or find a system in which I can find solutions to specific equations like this one or like this one, well, you don't have to sort of throw everything in. If all you're focusing on is solving a specific type of equation that can be viewed as setting a polynomial equal to 0, of course, if I want you to find a solution to this, it's the same as asking you to find a solution to the polynomial x squared minus 2 equals 0. Similarly, asking you to solve this is asking you to find a solution to the polynomial x squared plus 1 equals 0. If that's the task, well, we want to be able to do it in a more sort of surgical way, in a more precise way, without having to throw in all this other stuff that we might not be interested in. We might also want to do it in contexts other than the rationals. For example, it might be the case that we're interested in starting with z2 or z3, or coefficients coming from some finite field. The question might be, can you solve a certain polynomial equation where the coefficients come from a finite field? So maybe I'm going to ask you to solve this equation where the underlying field is z5. It's a perfectly good equation to try to solve inside z5. Can you do it or can't you? If you can't, how do you somehow enlarge the system so that you can? And so what we're going to call the basic goal for the remainder of the semester is this. We're going to hand you a polynomial. Well, that's exactly what we've been looking at. And we're going to be interested in the question of whether or not the given polynomial has the property that something in the original system, when you plug it in for x, spits out 0. Now if you go back, all of these equations that I looked at ask exactly that sort of question. Can you, given a polynomial, find something inside the system so that when you plug it in for x, that 0 gets kicked out? Well, for this one we could in z. For this one we couldn't in z. There was no 0 for this polynomial in, there was a 0 for this polynomial in z, namely x equals 4. There was no 0 for this polynomial in z, so we invented a bigger system. Inside this system, there is a 0 for this polynomial. It happens to be called 11/3. Here's a polynomial, x squared minus 2. Let's start with this one, the one that worked, x squared minus 9. Question, inside the rationals, is there a 0 for this polynomial? Sure, x equals 3. Also, x equals minus 3. Is there a 0 for this polynomial in Q? No. So what do? We invent a bigger system for which this polynomial contains a 0. Is there a 0 for this polynomial in the reals? No. But there is a 0 for that polynomial in here, inside a bigger system. So question, was this just some sort of historical, continuing to pile on the system that had been built all the way? Or is there maybe a more subtle or more precise or more, I use the word surgical, that's probably a good one here, sort of, direct approach to taking a polynomial and somehow building a bigger system in which the polynomial has a 0. So that's the basic goal. Basic goal, start with a field. I'm going to call the field, let me sneak a book, just because I want to be consistent with his notation. And I forget whether he calls the big field E or the big field F. Let's see. Yep. Yeah. Let's see. Yeah. Well done. That's why I don't have it in my notes, because he dances around it and doesn't use any letters for the notation. Okay, that's fine. Start with a field. I'm going to call it E for now. E. And let f of x be a non-constant polynomial in E bracket x. Think E is the field Q, rationals maybe, and f of x is the polynomial x squared minus 2, or x squared plus 1, something like that. Non-constant means it has degree at least 1. Well, folks, it might be the case that the given polynomial has the property that you can find something in the given field so that when you plug it in, 0 comes out. And I'm going to phrase that in terms of these evaluation homomorphisms in a minute. But for now, just think it might be the case that inside the given system that you're working in, you can find some value so that when you plug it in everywhere you see an x here, the 0 gets kicked out. Good example, x squared minus 9 in Q bracket x. Of course you can find some element that when you drop it in for x you get 0. 3 works. So does negative 3. But it might be the case that the polynomial that you started with doesn't have the property that you can find something in the original field and have a 0 get kicked out, like x squared minus 2, where the system is the rationals. Here's the question. Can we always find a bigger system, a system bigger than the one that we started with the property that the bigger system, well, contains the system that we started with, and moreover also contains something that you can drop into the original polynomial and have 0 come out? So then here's the question. Can we find a field, let's call it F, so that two things are true. First, the field that we started with lives inside the bigger field, and secondly, there exists, let's call it alpha, inside the bigger field for which when you plug alpha into the polynomial that you started with, that you get 0. In other words, for which when you do the evaluation homomorphism for f of x, that you get 0. Can can we, I'll say systematically, build a field with the property that, starting with a given polynomial with coefficients in, well, perhaps a smaller field, we may not have to build it anymore, but with coefficients living inside some field, that inside this new field, inside this extension field, that we find a 0 for the given polynomial. If you think, well, I already know how to do that and the Greeks told me how to do that, well, yes and no. At least the people that built the complex numbers over the centuries were able to do that as long as you started with a polynomial with coefficients in the rationals or eventually in the reals or eventually in the complexes themselves, but they didn't deal with the case that's actually going to be of great interest to us this semester and next semester. What if you start with a finite field? And it's also the case, again, that they really were looking more broadly when they built the reals and they built the complexes. It wasn't a case of, well, start with a specific polynomial and make it work. It was, well, can I make all polynomials that look like maybe x squared equals a works? Or maybe have all polynomials that look like x squared equals negative a work. So you get the reals or the complexes from there. And, you know, we've seen situations where we're able to answer this question significantly more precisely. If I hand you the rationals and I hand you x squared minus 2, let's just look at that one for a minute. Can you find a field that contains the rationals with the property that it also contains some special element so that when you drop that element into x squared minus 2 that you get 0 out? If you're thinking the reals or the complexes, that's not incorrect, but let me do one better. Look at the field S that you looked at for a homework problem, problem number 12 in section, I forget, 18 or 19 or something like that. The thing that looks like symbols of the form a plus b times the square root of 2. That's a field. Certainly contains the rationals. A plus 0 times the square root of 2, there are the rationals. And certainly contains the square root of 2. 0 plus 1 times the square root of 2. So there's a field that works. And boy, that's a whole lot more efficient than just throwing all the reals in order to answer the question, find a 0 for the specific polynomial x squared minus 2. So the main goal for the rest of the semester, the basic goal is come up with a method by which if you hand me a polynomial with coefficients in some field, if that polynomial maybe doesn't already have a 0 from the given field, extend the field somehow so that the new field actually does contain a 0 for the given polynomial. That's the idea. And this little historical trip was just meant to show you that really that process has already been done in one particular context, but it was done more from a global perspective. Find zeros for all possible polynomials of a given form rather than from a more local perspective. Here is a polynomial. Build a system where this particular polynomial has a 0. How do we do that? The answer is what we're going to do is build some structures. If we were building these structures from scratch, it would take us 3 or 4 weeks to do. But fortunately, these structures are ones that we've already seen before. What we're going to do is take these polynomial rings, f bracket x. Well, they are abelian groups under the addition. So it means we can talk about subgroups of that abelian group under the addition, which means that we can form the factor groups, which weren't your favorite topic, but they are nice and they're important. Well, we're going to do that again. But eventually what we're going to wind up doing is trying to put not only a group structure on these factor groups. Well, we know what that is. It's just going to be, coset addition. But we're going to also try to define a multiplication on these coset groups so that these coset groups become rings. And those are the places that we're going to try to find these fields. So what we're going to do both tonight and next Monday after the break is look at how we might go about constructing these things, these new rings, and asking when it is the case that these new rings actually become fields. And armed with that, we'll get enough information to try to figure out how we can go about, given a specific polynomial, building a larger field in which that polynomial has a 0. Okay. So, I'd write the word aside here because what we're doing is we're sort of taking a little detour, but the detour will take the rest of today and most of next Monday in order to build the machinery in order to answer this question. So it's more than an aside. Let's call it, a 75-minute detour or something like that. Detour. We need to look at specific construction. Of rings, which will look familiar. And here's what the construction looks like. So eventually we're going to be interested in doing this construction in the context where the ring we're interested in is f bracket x, is this polynomial ring. But we'll talk about the idea from a more general perspective. So start with any ring R, with any ring, I'll call it R. It's probably the case that the ring has unity, so I won't write that in explicitly, but it's probably the case that all of the rings that we'll wind up looking at are rings with unity. What we're going to do is look at a certain subset of the ring. And here's the definition of what that subset looks like. Definition is this. A subset, let's call it N of the ring R, is called an ideal of R. The Germans called these ideal subsets of R, and eventually the word subset got just thrown out for efficiency, I think, and the word ideal simply remained. In case N has two properties. First of all, well, remember the ring is always an abelian group under addition. And the first property that I'm going to require of this subset is that when you look at the subset under addition, that you actually get a subgroup under addition of the ring. Okay, so this is stuff that we did, weeks 1 through 8 in here. Here's a group under addition. Here's a subset. Is the subset a subgroup? Well, we know how to prove that. You just use the subgroup theorem, right? You have to show it's closed under addition. You have to show that the identity element's in there, and you have to show it's closed under additive inverses. This condition on the subset is usually relatively easy to demonstrate or to show or something like that. This next one is much more interesting. It's the condition that says this. If you take any element of the ring and every element of the subset, so I want you to take any element anywhere in the ring. I mean, this thing might be in the subset, might not, I don't know. Just grab your favorite one. Now grab your favorite element inside this subset. Then here's what I want you to do. Do this. I'll put a dot in there to emphasize that now I want you to combine these things under the multiplication. And I'm going to ask you to multiply them in the other order as well, because remember, in general, they don't commute. Most of the ones that we look at will have this equal to this by properties of commutativity, but in general, they don't need to be. And the requirement is that when you do that product, well, look, folks, because we're inside a ring, if you look at the product of any two things, necessarily you get something back in the ring, but what I'm going to require is that that product's always back in the subset. And the word we use to describe this situation is we say N has the absorption property. P, I don't know, B, absorption property. Meaning, if you multiply anything in the ring times anything in the subset, somehow that lands you back in the subset. That's what it means to be an ideal of a ring. Let's start with the two main types of examples. Example, let the ring be the integers, and let N be the subset consisting of multiples of 4. And it turns out that N is an ideal of R. Then N is an ideal of R. Bless you. So what do we have to check? We first have to check that if you look at the multiples of 4 under addition, that you get a subgroup of the integers under addition. Well, folks, we've done this a number of times. So check, already done probably 2 months ago. Take two things in here. I mean, how do you show something, subsets a subgroup? You just use the subgroup there. Take two things in here, add them. Do you get another multiple of 4? Sure. Is 0 in there? Sure, it's 4 times 0. If you have something in there, is it negative in there? Sure. If you have 4n, then it's 4 times negative n. So that's... All right, now, how about property 2? You have to convince me that if you take any integer, so let's call it z, and take anything that's inside the subset, let's call it 4L, if you do the product, z times n, you get z times 4L, which is 4 times ZL, because multiplication inside the integers is commutative. All right, that's fine. Oh, which is in the subset, because it's 4 times some integer. Now, I haven't written out all the window dressing with all the, with all the justification, but that's what's going on. If you multiply any integer by a multiple of 4, the point is you get another multiple of 4. I don't care what you started with as the first integer. 3 times 12 is still a multiple of 4. I don't care that 3 wasn't, as long as you... So the idea is that somehow multiples of 4 have this absorption property. Multiply any integer by a multiple of 4, you get another multiple of 4. And the other way, n times z. Well, of course, I don't really have to check it here, because n times z equals z times n inside the integers, because the integers happen to be commutative, but in general, we may not have a ring with that property. Okay, was there anything special about the number 4? Absolutely not. In fact, if I hand you any positive integer, heck, I could probably hand you 0 too, and I look at the collection of multiples of that integer, then I'll get an ideal. So more generally, let n be any integer. Then as usual, let capital N denote all the multiples of whatever integer you've chosen. In fact, folks, I'll even let you choose 0 here. Look at all the multiples of 0. There aren't very many, just 0 itself. Turns out that subset will work out just as well. Then n is an ideal of z. It's given a fancy name. It's called the principal ideal generated by little n. But I don't need that verbiage here. Okay? So the proof is essentially the same as above. Proof similar to the n equals 4 case. Above. So inside the integers, it turns out there are a lot of ideals. Hand me any number, and you'll get an ideal. Sometimes if you hand me two different numbers, they might produce the same ideal. For instance, if you hand me the number 3, or if you hand me the number 4, and ask me to look at all the multiples of 4, and your friend hands me the number -4, you look at all the multiples of -4, you get the same collection of numbers, the multiples of 4 and the multiples of -4. Why? Because 4 and -4, well, they only differ by, okay, negative sign, but we're going to use ring theory language here. They only differ by a unit. They differ by multiplication by -1, and -1 is a unit in the integers. It has multiplicative inverse. All right, but aside from that, what that result says is hand me any integer, look at all of its multiples, you'll get an ideal. Okay. Now, mumble under my breath. Turns out those are the only ideals. If somebody says I'm thinking of an ideal inside the integers, it has to be one of those. The proof is, it turns out we didn't write out all the details 2.5 months ago, but we could have proved that inside the integers, if you just ask what are all the subgroups, forget rings and ideals and stuff, what are all the subgroups of the integers? And the answer is they all look like n times z for some integer n. So, hey, it turns out that just getting past step 1 only limits the sorts of things that you have to consider to the n times z subsets, and it turns out they happen to have this absorption property as well. In other words, they happen to be ideals. Okay, here's the next big example. Guess what? If I've just given you an example that involves the integers, you expect the next example to be one that involves f bracket x, because we're trying to play up the relationship between those, and that's exactly what's going to happen. If the ring is f bracket x, here's what I want you to do. Pick any polynomial. I don't care. Pick 0 if you want. Pick a constant polynomial if you want. Pick, a cubic polynomial. I don't care. Let's call it little f of x in capital F of x be any polynomial. So pick any element you want. And now look at this set. Consider, I'm going to call it this, the set. Well, if I wanted to notationally write this set down in analogy to the notation that I used for the set over in the integers, I'd simply write little f of x times capital F of x. Just like I wrote little n for the integer written next to the ring I'm interested in, capital Z. And what did the notation mean over there? It simply meant look at all the things that were multiples of the thing that you started with. In other words, look at all the things that could be written as the thing you started with times something else in the system. That's what the multiples of 4 are. Start with 4 and you just multiply 4 times everything else in the system and see what you get. You don't get everything. You only get some things. That's what I'm going to ask you to do here. Start with your polynomial. Maybe it's x squared minus 2. And simply multiply it times every other polynomial in the system and see what you get. So this is what we're going to call it. It's also sometimes denoted by this, little f of x with round bracket or triangle brackets around it. And here's what it is. It's the collection of polynomials, let's call them g of x, that you can write as with the property that g of x can be written as little f of x times h of x for some h of x in bracket x. It's the collection of things that are multiples of that particular polynomial. Let's do an example. Example, for instance, if I want you to look at x squared minus 2, that's a polynomial in cube bracket x. What I want you to do is look at this set. Folks, there's no way I can write out everything in that set. Because what I'm asking you to do is simply take the polynomial x squared minus 2 and multiply it by whatever other polynomial you want and tell me what you get. Well, I'll give you one example. Okay, 0 works. Why? Because it's x squared minus 2 times 0. You get 0. And x squared minus 2 works because it's x squared minus 2 times 1. And x cubed minus 2x works because it's x squared minus 2 times x. And x, I'm going to not do this in my head because it's been a long day. Let's see. But, I mean, hopefully you see what I'm doing here. Just take x squared, multiply it by anything you want. Tell me what you get. Well, I happen to be able to get, what, plus x squared minus 2x minus 2. That's in there. X cubed plus x squared minus 2x minus 2, etc. There's lots of things in there. How do you determine whether something is in there? Oh, it's in there in case when you divide x squared minus 2 into it, that what you get is simply a polynomial with 0 remainder. So another way to view the collection of things I'm interested in is take the polynomial that you started with. In this example, it happens to be x squared minus 2. Divide that polynomial into the given polynomial, the one you're interested in determining whether or not it's in this set, and ask what the remainder is. If the remainder is 0, throw it in the set. If the remainder is not 0, then don't throw it in the set. Okay. So let's just put a big containment sign here. Contains all those things, but there's no way I can write them all out. Maybe for, yeah, hopefully this will be a little bit enlightening. I can tell you something that's obviously not in that set. Folks, if I hand you a polynomial of degree 2, there's only two possibilities. I either multiply that polynomial by 0, and I get that, or I multiply this polynomial by something that's not 0. And if I multiply by something that's not 0, what has to get kicked out is something at least of degree 2. So if I hand you a polynomial of degree 1, like x plus 3, it's not in this set. So there's a whole lot of things that aren't in the set, any polynomial of degree 1. There's also polynomials of degree 2 that aren't in this set. Like the polynomial x squared minus 3 is not in the set. Can you write x squared minus 3 as x squared minus 2 times some polynomial? Well, no. I mean, if you're going to try to rig a polynomial so that a polynomial times x squared minus 2 equals x squared minus 3, I mean, the polynomial has to start with a 1. In fact, it has to be 1 to make the leading coefficients match up. But if you're going to multiply by 1, you get x squared minus 2. You don't get x squared minus 3. So here are some things that aren't in there. For example, x plus 4 is not in there, x squared minus 3 is not in there, are not in this set in x squared minus 2. Again, the question of trying to determine those things that are or are not in there is going to boil down to some sort of division algorithm. So note, in this case, let's see, a polynomial, let's call it g of x, is in the subset of f bracket x that we've denoted by this, if and only if, or precisely when, r of x is 0 when you divide f of x into g of x. Right? And we've used, it turns out the notation is slightly turned around from the original usage in the statement of the division algorithm that we learned. But that's okay. I'm going to ask you to divide the polynomial that you happen to be given, which happens to be f of x here, into g of x. If the remainder is 0, then it's in that subset. If it's not 0, then it's not in the subset. Guess what the proposition is? Proposition, start with any such polynomial, look at the corresponding subset consisting of multiples of that polynomial, and then you get an ideal. So for any little f of x in capital F of x, this set, the collection of polynomials which can be viewed as multiples of this particular one, is an ideal of f bracket. Just as the collection of multiples of 4 always gave an ideal of the integers, or more generally, just as the collection of all multiples of a particular fixed given integer give an ideal inside Z, the collection of all multiples of any fixed given polynomial gives an ideal inside f bracket x. Proof, well, it's going to be the same idea. I think this will work out all right. Same idea as before, same idea as in the integers. Let's see. I have to first show that this set is in fact a subgroup of this set under addition. So what do you have to do? You have to take two things in this set. How about g of x, let's call this first one g1 of x, and g2 of x in the set. You have to show that the sum is in the set. So what does it mean? To say that the first one's in the set means I can write it as f of x times something, h1 of x, where h1 is a polynomial. It's just the definition of what this set is. It's the collection of things that can be written as f of x times something. And g2 of x can be written as the same polynomial, folks. This is the one polynomial that's common to everything. It's like factoring a 4 out. We're just factoring f of x out, times h2 of x, where h2 is in f bracket x. And so now add them. g1 plus g2. I mean, look what's going to happen. You just, I'll do two steps at once. You do, that plus that. Factor in f of x out. h1 of x plus h2 of x. It's no big deal. Which is in the given set. Why? Because it looks like f of x times something in f bracket x. That's what the first step of the proof of showing that this subset is actually a subgroup looks like. Show that it's closed under the addition. Is 0 in here? Can you write the 0 polynomial as f of x times some polynomial? Easy. It's f of x times 0. Boy, that was totally easy. Third, if you've got something in here, if you've got something that looks like a multiple of f, is its negative also a multiple of f? Sure, if you've got something that's written as f of x times h of x, then just look at the polynomial. It looks like f of x times negative h of x. Pull the negative sign out. You get its negative. So pieces 2 and 3 are easy. So eventually we get that this set with addition is a subgroup of f bracket x with addition. That part turns out to be essentially not an issue. Now for the second piece that we have to show in order to conclude that a subset of a ring is actually an ideal, the second piece is you have to show this absorption property. You have to show that if you pick anything inside f bracket x, what do you want to call it? I don't care. How about p of x? And you pick anything inside the subset, and you multiply them together, you have to convince me that the result is back inside the subset. So do p of x times g of x. Well, wait a minute. If g of x is in here, that tells me something. That g of x can be written as f of x times h of x. So this is then p of x times g of x is f of x times h of x. And technically I'm using associativity. And I'm about to use commutativity too, because p of x times f, I can switch those around. Because f bracket x is commutative. Oh, that's f of x. Oh, and I've used associativity again. P of x times h of x. Yeah, but look, folks, that's then f of x times something. And that's all you need in f bracket x. And so check. I mean, absorption turns out to be, in effect, the identical proof to the absorption property when we showed that 4z had the absorption property inside z. You multiply something by a multiple of 4, you get another multiple of 4. If you multiply a polynomial by something that's already a multiple of f of x, you get a multiple of f of x. I mean, the arithmetic inside z and the arithmetic with these polynomials share lots of common properties. That's just one of them. Now, technically, I have to show that if I multiply them in the other order, that I get something in the subset. But again, we're working inside a commutative ring, so once I've shown this one, then this one, in the context in which we're working, comes for free. These are ideals. Let me talk you through where we're headed, and then I'll hand you a homework assignment, which won't be due for a while. I'll be doing a week and a half. And then we'll get out of here. Look, anytime you have an ideal, well, ideal sits inside this group as a subgroup, but the hypothesis on the addition inside a ring is that this is always commutative. So by default, as soon as you have a subgroup of a commutative group, it's necessarily a normal subgroup, because any subgroup of an abelian group is normal, which means that we can automatically form this factor group where the operation is addition. And the question is going to be, is it possible to turn this group, which will be an abelian group under addition, just factor, coset addition, can we turn this into a ring? You're thinking, well, R is a ring. Can we somehow use the multiplication inside R to turn the cosets into a ring by defining some sort of multiplication? And the answer is, in general, no. But if the subgroup happens to have this second property, this absorption property, then the answer is yes. And that's why we're going to need this second property in order to eventually make the factor group, the additive coset group, into a ring. And then the question is going to be, all right, once we form those rings, some of which you're familiar with, for instance, when we start with r equals the integers, these will just look like z mod n or z sub n. So we already know what those look like in that one particular setting. The question is going to be, what do those look like if we start playing this game in the situation where r is f bracket x and n is one of these ideals generated by a polynomial? What do the structure of those things look like? And that, in effect, is what the basic goal and its answer will lead us to. Okay. All right. So here is home. This will be the next to the last homework assignment that I'll give you for the semester. It'll be due, on normal homework schedule, so Wednesday, November 28th, so the Wednesday after the break. And here is the stuff I want you to look at. In section 26, problems 9 and 11 through 15, I only want you to turn in 2 of those, 12 and 13. But then I'm going to hand you 3 extra problems, and these are each related to the other. So once you get one, the others should follow relatively immediately. So, and these 3 additional problems. First, if I is an ideal of the ring R, and it happens to be the case that the unity element of R is inside the ideal, then show show that the ideal is actually the whole ring. Show that I equals R. That's one. Two, if R is a field, show that its only ideals. Its only ideals are 0 and R. And the hint is use problem 1. Use the result of this. And then third, inside the integers, if I hand you two integers a and b, I can form the ideal consisting of all the multiples of a. That's an ideal. I can form the ideal consisting of all multiples of b. That's an ideal. And what I'm going to ask you to do is look at the intersection of those two ideals. It turns out that's an ideal. In fact, it turns out that it's the ideal consisting of all the multiples of some fixed number. And the question is, what is C in terms of A and B? Terms of A and B. And that's, I guess, 3A. And part 3B is the same sort of question. Take two integers, I'll call them C and D, I guess. Yeah, I'll call them E and F. And what I want you to do is add everything inside the multiples of E to everything inside the multiples of F. You get a subset. And in fact, you get a subset that looks like all the multiples of some fixed integer G. And the question is, what is G in terms of E and F? So take the intersection of two ideals of this form. It turns out it is an ideal of the same form. Tell me what the and the way I want you to do this, folks, is just write out a number of examples, write out 2 or 3 examples, and you'll see the pattern after a while. I'm not worried about the actual proof of this result in general. Just get to the answer for me. Okay? And I'll have you turn all these in. So these are all turn-ins. Okay. All right. If you happen to have the homework that's due tonight, that's great. Just leave it on the table here. If you don't and you want to turn it in by tomorrow at 5, that's fine as well. Just either fax it in or the preferred way would be to send it to me as an attachment to an email. Remember, after the break, so a week from tonight, we're meeting in Dwyer 121. And if I don't see you before and if I don't see you tomorrow, please have a safe holiday, and I'll see you a week from tonight. Issue is this. If you look at the non-zero elements, look, 17 is prime, so Z17 is a field, so the non-zero elements form a group under multiplication. That group has 16 elements in it. Is that a cyclic group? Well, if somebody just hands you a group with 16 elements and tells you it's abelian, there's absolutely no guarantee that it's cyclic. But what will be shown, we won't do it this semester, but we will do it next semester. If you come back for another dose, then you'll find that if you take any primes and you take the field Z sub that prime and you throw out 0 and you look at the corresponding abelian group, that group is always cyclic. So what you're trying to do is find a generator for this under multiplication. That's the question. The other way to phrase it is, in other words, take the units of Z17. And as soon as you're told that you're supposed to be looking at the units of Z17, it means you're throwing out 0. And so necessarily you're looking at times as the operation. A couple of you just convinced me that Z17 under addition is cyclic, and that certainly could have been done about 2 months ago. You just write down the number 1 and show that if you keep going, you get all the elements in Z17. So a couple of you misinterpreted that question. The other one that caused some of you some grief was the last one. In effect, what you're asked to do is this. Take the following function from a polynomial ring to another polynomial ring, the function that what we call formally differentiates polynomials? Well, you come into the table knowing something about differentiation, but only in a situation where the coefficients come from the real numbers. And in that particular situation, differentiation of polynomials is just one of many differentiation ideas that you can talk about. You can talk about, differentiation in the context of exponential functions or trigonometric functions or whatever it is. And just as one sort of byproduct of differentiation happening to mean limit as h goes to 0, blah, 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 you happen to get this particular formula for polynomials. But the point is that formula can be thought of as a formula that applies to any polynomial over any field of coefficients. Take a polynomial and simply associate it with this other polynomial. Take the polynomial a0 plus a1x plus a2x squared plus da-da-da-da-da and associate it with, I'm just going to make this thing up, a1 plus 2 times a2x plus 3 times a3x squared plus 4 times a... Makes sense. The fact that it happens to be apparently interesting because it happens to be this byproduct of a formula that comes from a limit is that if you take something that's in the kernel, then necessarily a1 is 0, a2 is 0, a3 is 0, etc. up through an is 0. In other words, if you have something in the kernel, then all this stuff has to be 0 because we've just proved that each of the coefficients is 0. So if you have something in the kernel, it has to look like just that. In other words, it has to be a constant. So essentially, all of you got to the right place, but you didn't use the place where the characteristic of the field is 0 appropriately. Okay, now for part C, I'll go through this one a little bit more quickly. Most of you recognize that the image, in other words, what actually gets spit out of the derivative, is every possible polynomial. In other words, you told me the image is all of f bracket x. Well, that's true. Let's see what happens in the reals. If you hand me a polynomial, you have to convince me there's some other polynomial whose derivative is the one you started with. That's what it means to convince me that the range is all of f bracket x. Just as an example, if I hand you x squared, can you build me a polynomial whose derivative is x squared? Yeah, integrate. 1/3 x cubed works. I mean, 1/3 x cubed plus 7 works. There's lots of different integrals. But just write down an integral. 1/3 x cubed. Derivative of 1/3 x cubed is x squared. So x squared is in the image. X to the fifth. In fact, x to the n is in the image because I can write down something whose derivative is x to the n. 1 over n plus 1, x to the n plus 1. I'm just integrating. So you take the derivative of the integral and you get right back where you started. So that all seems well and good, except for what? Except for how do you know that 1 over n plus 1 times x to the n plus 1 makes sense? In particular, how do you know that 1 over n plus 1 is a legit thing to write down? I'll ask it one more way. How do you know that 1 over n plus 1 isn't 1 over 0? And the answer is because the characteristic field is 0, that n plus 1 is not 0. So the punchline is, because we have a field of characteristic 0, we can, quote-unquote, integrate any polynomial. So the point is that for part C, to show that every f of x is in the image of D, image of the derivative, if f of x is blah, 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 then, so as above, then write down this. G of x as, what is it, a0x plus a1 x squared over 2 plus a2x cubed over 3 plus an I've just, in some sense, artificially pulled out of thin air some polynomial. This is in f bracket x. The reason it's in f bracket x is because each of these symbols makes sense because none of them requires me to divide by 0 because none of the denominators are 0 in f because the character. I still can't believe they scheduled a game at night. numbers.
Yeah.
Yeah, they got really lucky, like by about a day, I think, 'cause it's supposed to get really bad. I don't know.
How much do you care about this?
It's just tough. I don't know about most. Somebody, I'm sure. I'm sure they're nice people. And their mothers love them. Okay. I'm sure. Let's see. Ashley, no. Lindsay, no. Lindsay, no. She's Jessica. Here you go. No. Lonnie, go. No. Richard. Thank you, sir. Jared. See, Jared. Will. Sarah. Go. Diana. Devin. John, no. Okay. Okay, let's see. Chris, no. No. Okay. Not too bad. A couple of quick comments on the assignment coming back. Most of them were pretty computational, so didn't cause too much grief. The only issue that came up on the more computational stuff is what that one question asks you to do is find a generator for, not for Z17. Well, I know what a generator is for Z17 as an additive group. Just one works because 1 plus 1 is 2. 1 plus, so that's not an issue. What is at issue expression? Okay, just happens to be. But folks, this formula has nothing to do with limits or anything. It's just do it. And with that in mind, the question then becomes part A, is this a, well, is it a homomorphism where the operation is addition? You're thinking, well, you know, if I was working over the reals in the particular case where the field is R, then yeah, because the derivative of the sum of two functions is the sum of the derivatives. There's an addition rule. Question 1, part B was, is the derivative function somehow a multiplicative function? In other words, is the derivative of f times g the derivative of f times the derivative of g? And you should have been thinking right away, well, no, because derivatives and multiplication don't work out well. There is the product rule that doesn't say just derivative of f times derivative of g. And most of you recognize that. That's good. Some of you wrote this sort of flowing prose about how it shouldn't be, and it's not, and there's not a prod, blah, 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 blah. But just, folks, give me a counterexample. Just write one down, and you're done. That's all you need. Okay? All right, now, parts B and C were interesting. I guess I should have known that I'd get this. You know, I mentioned in class, well, you need to use the characteristic of the field as 0 in parts B and C, and some of you just started off parts B and C saying because the characteristic of the field is 0 and just went on and basically didn't at all use the characteristic of the field is 0. It's all right. Or some of you sort of put it in, but it sort of appeared at a place that indicated that maybe you weren't really using it in a way that was, that compelled me to believe that you understood what was going on. Here's the idea. What things are in the kernel of the derivative function? That's the idea. And if you come to the table thinking, well, I know what things the derivative function kills. The derivative kills constants. Perfect. Okay, it's just we're taking the derivative in contexts that are larger than the one that maybe you're used to working with. You're taking derivatives in the context that isn't just r bracket x, which has a certain set of properties associated with it. You're taking derivatives presumably where the field could be anything of characteristic 0. Maybe the field's the complex numbers. Maybe the field's the rational numbers. Maybe the field are some other fields that we've seen. For instance, this thing that we called S, the a plus b root 2 field. So how do you know that the only thing that gets killed in that context are the constants? It's not anything to do with a limit process anymore. And the answer is this. Just write down what it means for something to be in the kernel and convince me that it has to be a constant. So what does it mean for a polynomial to be in the kernel of the derivative function? It means if you write f of x as a0 plus a1x plus a2x squared plus an x to the n, that's what it looks like, then the derivative is, well, it's a1 plus 2 times a2x plus 3a3x squared plus et cetera, plus n x to the n minus 1. There's the derivative. No problem. And the question is, what does it mean to say that the polynomial is in the kernel? It means that the derivative is 0. Equals 0. That's what it means by definition of it being in the kernel. So look, I have this polynomial equaling this polynomial. So all the coefficients have to be the same. That's how two polynomials are equal. Well, let's see, the coefficient on the constant term over here is a1. The coefficient on the constant term over there is 0. So we get a1 is 0. The coefficient on the x term over here is 2 times a2, and the coefficient on the x term over there is 0. Coefficient on the x squared term over here is, and the coefficient on the x term over there is, et cetera, et cetera, et cetera. The coefficient on the x to the n minus 1 term is that. The coefficient on the x to the n minus 1 term on the right side is 0. I mean, obviously, they're all 0 on the right-hand side. So I'll say equate coefficients, because that's what it means for polynomials to be equal. So here's what this says. If f is in the kernel, then necessarily the constant term is 0. Okay. Oh, I said that wrong. If the derivative is 0, then necessarily the linear term is 0. In other words, the term that's being multiplied times the x term is 0. If f is in the kernel, it means that 2 times a2 is 0. Question, does that imply that a2 equals 0? I'll give you a hint. And I'll give you a hint. Use the hypothesis. Why? Look, if you have the product of two things equaling 0, any field's an integral domain, so one or the other has to be 0. Is this equal to 0? No. Why? Because the characteristic of the field is 0. 2 is not 0 in our field because we're told that inside this field, if you take 1 and you keep adding it to itself, you never get 0. In particular, 2 isn't 0. So it implies a2 is 0 since the characteristic of the field is 0. How about 3 times a3? So that's 0. Does that imply a3 is 0? Sure does. Why? Because the characteristic of the field is 0. I have n times an is 0. That implies that an is 0. Why? Because the characteristic of the field is 0. So here's where you're using the hypothesis. So what we've just shown